broadcasting. Okay, I guess everyone got the message that this is live stream.
So Inar, can you create the breakout rooms also?
Yes, I'm doing that. So so maybe you can check. I created four rooms, and everyone can in principle enter the room.
You already did that?
Yeah, but I need to open them. Yes. Okay. So.
While you are doing that, to whom should we send the talks? You know, you wanted the files, PDF or something like that.
You can send to either to our personal emails or to this early universe at epfl.ch. We check all accounts.
I guess you do not all want to have all the talks, no?
You can send to me. That's yes, it will be easier to have just one option.
Hi, Valery, at this occasion.
Hi.
I'm seeing you.
Hi, Christoph. It's nice seeing you.
Okay, so so these waiting rooms. So what are these rooms that you just opened?
So in principle, they are for discussion.
Look, let's make it in order because Sebastian will explain all that.
Yes,
right?
yes.
Okay, so I think it's time to start, right?
Yeah.
It's 10:12. We were supposed to start at 10:10. Okay, so hello everybody to the online workshop Physics of the Early Universe. Okay, so this workshop is organized by Andrei Shkerin in our Timirasov, Sebastian Zell, and myself. And Andrei, Inar, and Sebastian, they did all the work clearly. Okay, so let me tell you what we want to discuss here. So the workshop will run from today, June 13, to Friday, June 17. There will be one virtual lunch break, 1.5 hours, which can be used for real lunch and also for discussion, and one virtual coffee break with time for questions and discussions. So the topics of the workshop, they cover early universe, quantum cosmology, inflation, preheating, phase transitions and vacuum decay, leptogenesis, Big Bang nuclear synthesis, primordial gravitational waves, dark matter, primordial black holes, and related topics. So we wanted to have 1,000 participants, but we failed miserably. We got just 999 after the deadline. Okay, so maybe, but there isn't, nobody can register anymore, afraid. So we will skip to this official number. Okay, so the program of the workshop follows more or less the way how the universe evolves. So we're going to start from inflation, and we're going to end by the events which happened later in the universe. So you can see this program on the website. And we will start the morning session with Rubakov, Senatore, and Turok. So welcome to everybody. We look forward very much for the talks, discussions, and collaboration which can result from this event. Okay, and now Sebastian will provide different, very important explanations.
All right. Okay, so about the procedure. So talks are supposed to be, so the talk slots are 40 minutes, and it's roughly supposed to be 30 minutes for the talk and 10 minutes for discussions. And then, as Misha said, we're expecting a large number of participants, and that we're already kind of seeing that. And so by default, you cannot unmute yourself, but only we can unmute. And so if you have a question, you raise the hand, and then we unmute you. And also, we'd like to postpone questions till the end of the talk. And then we will leave the room open throughout the day, so during the lunch break and during the coffee break. And so this is an opportunity for informal discussion. And in particular, we encourage the speakers to stay until the next break. So the 3 morning speakers until the lunch break, the 3 speakers after lunch until the coffee break, and the speakers after the coffee break until the end of the day. And then participants who have more questions and want to discuss informally with the speakers can stay till the break, and then have a more informal discussion about the talks. Also, so Gia asked what are the breakout rooms for. So these are meant to be separate discussion rooms. So no one will be assigned there, but you can join there freely. And so maybe you can arrange with the speaker to meet in some of these discussion rooms, or you just meet a friend there and have some informal chat. So you can join yourself the breakout rooms, and you can just do that to meet someone and to discuss in private. Also, chat is fully enabled, so there's the public chat. So of course, if you have something you want to tell the whole audience, or maybe it's more convenient for you to ask a question in written form, then you can do it in the public chat. Also, there's private chat, so you can chat to another participant. And in particular, we encourage you to contact us also. So one of us has the account that is called Workshop Organizers. So that is Inar at the moment. And then if you have any question about procedure or where's the recording or something, then you just write a private message to the workshop organizer. Also, we have the asynchronous discussions. So we have a Mattermost. So if you're interested in that, feel free to join. So the invitation link we send in the email of Saturday. If something doesn't work, then please tell us. Also, the talks will be recorded unless the speaker does not agree to that, and they will be made public later on our YouTube channel. All right, and with this, I hope you will enjoy the talk, the talks and the workshop. And I'm going to hand over to Misha, who will chair the first session.
Okay, thank you very much, Sebastian. So now I invite, we are starting the workshop, and together we're starting the workshop. We are starting the universe from strong gravity regime. So Valery, please share your screen and go ahead. And now we don't hear you because you are muted, I guess.
Is it okay?
No, now we hear you.
Okay, so it's nice to be virtually in I don't know, Lausanne probably. But anyway, I'm glad to see everybody here, and let me start. Okay, so let me start. So I'm going to talk about the rather unusual way of thinking of the beginning of the universe. And this business is in collaboration with Yulia Ageyeva and Pavel Petrov at our institute at Moscow University. So as an introduction, what I'm going to discuss is, first of all, homogeneous and isotropic universe, but without initial singularity, which is the ideas, the scenarios are bouncing scenario where you have the universe that contracts first and some miracle happens and the expansion of the universe begins, or genesis, when the universe starts empty and flat, and slowly the energy density, so to say, builds up, the expansion of the universe becomes faster, and at some point in all these scenarios, you have to transit to conventional hot epoch. Motivation for that is, first of all, curiosity, because of course we know that there is a very nice theory which is inflation, but it's always good to have alternatives, even to comparing scenarios. Second is that it's nice maybe to have no initial singularity, but I will discuss what may come again as a replacement of the initial singularity. And then, of course, there is this set of problems that inflation nicely solves, horizon curvature, etc. Here, it's mostly, for the time being, solved, so to say, by assumption about the initial state. So it's not a real solution, but it's sort of, you move the problems away to minus infinity in time, basically. One nice thing about this is that it may happen that you have very long prehistory of the universe governed with something which is not conventional method energy density or dark energy density. And that's useful for trying to relax the cosmological constant. If you think of relaxing the cosmological constant, you certainly need very, very long period of time to do that, to relax it to a very small number we have it. Of course, one has to think about the generation of a correct power spectrum of scalar perturbations, and also worry about the generation of tensor perturbations, about gravitational waves. This is not so automatic in these kind of scenarios, of course. Now, as again, an introduction, there is an obstacle in classical general relativity for both of these scenarios, genesis and bounds. If you stick to general relativity, then you need exotic matter that violates the null energy condition. Null energy condition meaning that the energy momentum tensor contracted with arbitrary null vector is positive. That's the null energy condition. And if you want to violate it, then you have to have strongly negative pressure, more negative than energy, minus energy density. And that's not very easy in conventional field theories or meta theories. If you want to go further and consider modified gravities, like scalar tensor gravities, then instead of the null energy condition, you think of null convergence condition, which relates geometrical number, geometrical quantity, the Ricci tensor, and again, the same story about its positivity. Now, if the null energy condition or null convergence condition is not violated, then there is a Paneros theorem that says that in the expanding universe with which is large enough, where the spatial curvature is negligible, there was necessarily a singularity in the past. So you do need to violate the null convergence condition. And it's known for quite a while that one set of theories where the null convergence condition can be violated is the class of Herdesky theories, which are the scale tensor gravities which contain both metric and the scalar field, which are called pi. So it's a scalar tensor gravities. And it's known for quite a while that it's straightforward to construct healthy bounds or genesis stages. However, there is a problem with Herdesky itself. Namely, if you want to construct complete cosmologies that start from -infinity back in time and go further to today and further out, then it's not possible in Herdesky without pathologies. And pathologies are either ghost or gradient instabilities in the background, which may happen pretty long before or after bouncing stage, for example, but they do happen. And let me describe briefly what are the reasons. The reasons are pretty technical. So here is the, do you see my pointer? No?
Yes, we do.
Okay, very good. So this is the general Herdesky theory. F is often called G2, K is often called G3. So there are 4 arbitrary functions of the field and its gradient term, its kinetic term. There are 4 functions, and they are arranged, the Lagrangian is arranged in such a way that the field equations, both gravity equations and scalar field equations, are all second order, even though we have higher order terms in the action. That's the peculiarity of Herdesky theories. So we are, as a remark, we are going to live in Jordan frame all the time. So there is an entire, set of arbitrary functions in this sort of theories, and you can arrange this in such a way that you get healthy bounds, for example. However, there is a no-go theorem, saying that there is a ghost or gradient instability at some stage if you consider the entire evolution of the universe. And the argument goes like this. If you choose the unitary gauge, which I will use quite often, then the perturbations in the theory about a given homogeneous isotropic background are parameterized by the scalar zeta and the tensor part, transverse tensor Hij. These are the only dynamical variables because the left and shift functions are not dynamical. You have, the second order equations. So if you do your machinery and solve for the constraints, you find, of course, quadratic Lagrangians for these perturbations, which, as usual, have the standard forms with spatial derivative squared, gradient squared, and time derivative squared, both in scalar and in tensor sector. And let me notice that these coefficients here are effective Planck constant squared. That's going to be important for me. Now, for the stable background, you need all these functions of time positive, and then you don't have any gradient instability or ghost instability. Now, what are the formulas for them? Let me give you simple formulas for, in the case of when one of the free functions is set equal to 0 in the Herdesky Lagrangian, then the result is pretty simple. Simply looking, to scare you to death, I wrote, in this even simple case, pretty complicated formulas for entries in these expressions, but I will not use them at all. Now, the key relation here, which is here, this is the middle of the second column, there is a key relation. The key relation is that the sum of the two coefficients, which must be positive and which are effective Planck masses, the sum of these two coefficients make a total derivative, which is a positive numerator and some denominator. Okay. Now, if you don't want a singularity in your cosmology, then the psi should not cross zero, because theta is a combination of the Lagrangian functions, etc. And if it's infinite, then it is a singularity. So psi is that comes in the derivative here, time derivative here, is a thing that shouldn't cross zero. However, this contradicts the upper red line, because if you write your difference between the finite and the initial psi, then it's of course an integral of the right-hand side here. And if you stick to the case when this integral diverges at both minus and plus infinity, I recall that A of t is constant or increases towards plus and minus infinity, and f of psi, f are Planck, effective Planck squared, Planck mass squared. Then if you say that this effective Planck mass squared stay constant all the way from minus to plus infinity, then these integrals are indeed divergent, and immediately you find that you can't have this psi not crossing zero. This psi should be negative at some point, at some time, and positive later on, or inversely. Well, okay. So, so there is no go theorem. You can't reconcile positivity of these functions, which is necessary for coefficients, which is necessary for stability, and the explicit expressions for them. This is a no-go theorem. Okay, now, can one get around this theorem? Of course, one can. This theorem has its own assumptions. One is that we are in Herdesky theory, but we know that there are other apparently healthy theories which are beyond Herdesky and Host, and for them the no-go theorem doesn't hold. And one can indeed construct balancing or genesis cosmologies using the beyond Herdesky or more general Host theories. However, there is an issue there, and the issue is that once you add the luminal apparently extra scalar field, then you get necessarily superluminal propagation. So beyond Herdesky and Host have their own problem with superluminarity. What I'm going to stick in this talk is the other way out. Still in Herdesky, I will stick to Herdesky, and I will violate one of the assumptions. And one of the assumptions is that all these functions should be finite, bounded from below by positive number all the way to minus infinity. So I will consider the case, well, when all these coefficients, remember these are effective Planck masses, all of them tend to zero at asymptotic minus infinity. So, and then in this way, I violate the necessary condition for the no-go theorem, because my integral, I can arrange my integral in such a way that it is convergent. And if it is convergent, then the no-go theorem doesn't work. However, and indeed you can construct the models of this sort where you have no singularities or instabilities altogether. However, this is tricky because the effective Planck masses vanish at minus infinity. So gravity becomes strong, and there is a danger of strong coupling. So people sort of dismiss this option for some while because there is a problem that you have very strong gravity in the past. Let me give you an explicit example. An example of the initial stage of a bounce. You have a contracting universe. Time runs from minus infinity. The scale factor decreases. This is the initial stage of the bounce. So you can arrange functions. You have the functional freedom in Herdesky Lagrangian in such a way that this is indeed a background solution. And furthermore, it's healthy, and then bounce itself is also healthy. And then you can cook up a model where you have, say, kination stage domination of massless conventional scalar field a la K inflation in the end. So it's pretty straightforward since you have the functional freedom in your Lagrangian to construct a viable model without any pathologies and with such a behavior of the scale factor and Hubble parameter in the contraction states in the journal free. Okay, now I write the action for perturbations again, and this is the part of the action which is scalar. This is the part of the action which is tensor. And in this particular kind of models, you have your functions, your coefficients that decrease as we want as you go to minus infinity. Okay, and that's exactly what we want for prerequisite of the absence of instabilities for convergence of this integral. So you can do that by choosing appropriately the parameters in your model, this mu and the alpha, which is the coefficient of the Hubble parameter, or a power for in the scale factor, so this integral can be convergent. You get rid of the no-go theorem, but again, there is a problem with strong coupling, probably. However, one can think more carefully about what's going on, because this is quadratic Lagrangian. If you look at the cubic and higher order terms and perturbations, they are also suppressed at large negative times, at asymptotically as an asymptotic past. So both the strong coupling scale itself, the quantum strong coupling scale that you can infer from these cubic terms, also depends on time. So now the question is, you have a classical time scale or energy scale, inverse of time, and you also have quantum strong coupling scale. Now, what is the relationship between them? So gravity is strong in the past, but does it ruin the classical description of the background and, all the rest? Can one trust the classical theory of the cosmological evolution? So again, we have the classical energy scale, which is inverse of the time, which is Hubble or Hubble dot over Hubble. These are the classical energy scales. And you have to figure out what is the strong coupling scale inferred from the interactions of my perturbation between themselves. And of course, if your strong coupling scale, quantum strong coupling scale, is much greater than the classical scale, then you're in business. So let me give you a simple example. Explicit example is in tensor sector. I rescale at a given moment of time, I rescale my spatial coordinates to set A equal 1, and then, or in other words, I work in terms of physical momenta, spatial momenta, and then what I have in the tensor sector is the quadratic part again, and in fact, the coefficients are the same here in the gradient and temporal term, and there is also interaction which is governed by the same function. So to figure out the strong coupling scale, you simply canonically normalize your field, your quantum field, and immediately you find that in terms of canonically normalized quantum field, your coupling constant is here. It's again the same parameter that the same Planck mass squared, basically, nothing peculiar. Now, there is a dimension 5 operator, of course, and from that you immediately figure out what is the strong coupling scale. The strong coupling energy scale is given by the square root of this function, and remember, in our model, it is given by this expression here. When it goes to 0, but it goes to 0 like 1 over t to power mu. Okay, so if you compare this to the classical energy scale, which is 10 to minus 1, you figure out that the strong coupling scale is actually much larger than the classical energy scale. So your classical description is very well valid. The effective Planck mass is much, much larger than the energy scale of classical evolution. Or in other words, effective Planck time is much, much shorter than the Hubble time. So then you can, of course, this is a simple example, a simple argument, but then you can do the whole machinery and go to study tensor sectors and scalar sector and all orders and perturbation theory. This is not so immediate, of course, because you have to study the whole perturbation theory, but the outcome is this. The outcome is that the ratio of strong coupling and classical scales indeed goes to infinity in the asymptotic past, provided that this parameter mu is smaller than 1. And I mean, depending on the process you consider when discussing the strong coupling scale, there are positive parameters here, but it doesn't really matter. All strong coupling scales become much greater than the classical energy scale at large negative times. So in the large region of parameter space, classical field theory treatment of cosmological evolution is legitimate, even though you have effective Planck masses tending to 0. So the overall picture is that the universe starts at very low quantum energy scale. The effective Planck mass is very, very low, asymptotically vanishes as time goes to minus infinity. But it expands so slowly that the classical expansion rate is much longer, the expansion time is much longer than the effective Planck time. Both tend to 0, but classical time is longer. So this is rather an unusual situation because in this case, the gravity looks like the strongest force in nature, which is the opposite to what people try to claim. You can do this for genesis as well, not only for bounds, but for genesis. Now, let me probably give you an example of concrete Lagrangian when it happens, where such a phenomenon occurs. And the easiest way to do that is to use the ADM formalism instead of the Lagrangian formalism. And in the ADM formalism, it's very well developed. It's very convenient, actually. You use the ADM form of metric with perturbations in it, or general ADM form of metric, and choose the unitary gauge from the very beginning, where the scalar field, say, increases linearly, although you can choose any other. So the field variables are all in metric, and the Lagrangian or action is written in terms of metric. Okay, here it's written, instead of the original 3 functions, I'm sticking to the case when G5 is 0, instead of original 3 functions in the Lagrangian formalism, you have 3 functions in the ADM formalism. These are A1, A2, A3, and 4. And there are terms that contain extrinsic curvature of constant time hypersurfaces. It's written here, and it's trace. So you trade your Lagrangian functions in the Lagrangian formalism in the covariant formalism to these three functions in the ADM formalism. And there are very well defined conversion formulas between the ADM and Lagrangian formalism. Now, this is useful because the homogeneous field equations are simple, so simple that you can easily sort of understand what's going on. So let me give you a concrete example of contraction before the bounds. So early time of contraction before the bounds. So I choose my functions in this way. This is my mu, the same parameter that I used before, but now they are, the functions depend on time explicitly, and the lapse function. So I choose these, the arbitrary functions in such a way, and I should mention that in terms of the original functions, these are not so simple. They are rather complicated expressions, especially because you have logarithmic terms there. But in terms of this ADM formalism, it's very convenient. Now, the point is that you have an overall coupling here, G, which I introduced here, and it will play some role later on. But otherwise, you have all numbers A1, A2, A3, A4 to 1, and my mu is, a parameter in my Lagrangian. Also for the 1. Now, the homogeneous solution is simply that the lapse function is a constant, and the scale factor indeed decreases as time goes from minus infinity to become smaller. The scale factor decreases like power. Okay, and you have algebraic equations for this n and alpha. Now let's go to cosmological perturbations. I wrote again the Lagrangians, quadratic Lagrangians, and it turns out that once you do the calculation, that the tensor and in the tensor sector you have simple behavior like this. Remember, again, there is an overall coefficient here, the strength of the Herdesky theory. This is G, and also the scalar coefficients have similar form. But if in the case of tensor perturbations, you have units outspeed, they propagate luminally, the scalar perturbations do not. The scalar sound speed is not equal to 1. They can propagate subliminally, and that's important. And this is a sort of analog of power law inflation if you look at the Lagrangian here for perturbations, then the perturbation coefficients of perturbations are actually power law functions of time. Okay, so it looks very much like the perturbations in the power law inflation. And indeed, you can look at this perturbation Lagrangian, go to conformal time, get the Lagrangian of this sort for tensor perturbation, for example, get the Lagrangian of this sort, then you can see that the coefficient here, a square times the G tensor, is effective a squared in terms of the conformal time. And it goes like here, so it's power law behavior in terms of conformal time. And if you use effective, and that's of course effective, that's an effective scale factor for the perturbations. So if you introduce effective physical time for perturbations, then you indeed have power law inflation. The perturbations behave exactly like the perturbations in the power law inflation for tensor modes, for example, in particular. The power law inflation with such a power law, effectively. So this tells you that, well, first of all, there is a kind of mismatch. Mismatch is that we needed mu less than 1 to have a healthy classical behavior at -infinity, but here mu is assumed to be larger than 1. What happens when mu is smaller than 1? It does guarantee weak coupling all the way to -infinity, but the effective matrix actually describes accelerated acceleration at the beginning of the big rip. So, and immediately you understand that you're going to get the wrong spectral tilt. So there is a sign of tension. Let's consider this in detail. So,
Valery, we talked for half an hour. So,
I did.
Yes.
Oh, okay. Okay, let me make a long story short then. First of all, I can calculate the power spectra for perturbations generated at the early stage of the cosmological evolution. And I have a couple of problems. One is that I have red tilt, which means that I need to have this parameter mu greater than 1. And then that's interesting. That's interesting, meaning that this parameter either has to be time dependent, or another option. Another option is that the theory may dive out from strong coupling regime, so that my gravity is strongly coupled indeed, and somehow the universe starts from the really quantum gravity regime. The second problem is with small tensor to scalar ratio, which we know from experiment, and this is achieved by choosing the spectral by choosing the sound speed much less than 1, which is similar to K inflation. And there is tension, which I will not go into detail. The tension is that you, on the one hand, you want to have a healthy perturbation theory. You don't want to be in the strong coupling regime of strong gravity regime, the sub-Planckian regime at early times, and on the other hand, you want to generate perturbations with small spectral tilt and small R ratio. So let me not go into detail. Let me just say that if you do a back of envelope calculation, then there is a relation between the tensor to scalar ratio R and the scalar amplitude, and the overall back of envelope estimate gives you that the tensor to scalar ratio must be greater than some power of the scalar amplitude, and it is just on the border, roughly speaking, to be correct for known values of R. Okay, so you need precise calculation, and that's what we are doing now. We are trying to figure out whether you can reconcile everything and construct a viable model with a correct spectrum of scalar and tensor perturbations. So let me summarize. The bounds and genesis within Herdesky theories with strong gravity in the past appear viable scenarios. We didn't find any pathology so far. We can get correct spectra of cosmological perturbations with probably certain fine-tuning to ensure that the parameters are small, R and S is close to 0 to 1. And it seems that the tensor to scalar ratio cannot be arbitrarily small, otherwise you go into strong coupling problem. And while one notices that scale and tensor spectral tilts are equal for the power law of initial contraction, which is different from conventional inflation. And what seems to be an interesting property is that there appears to be, in any case, strong coupling nearby. Nearby meaning that the interaction terms in the Lagrangian are not that small, so you might suspect there is a strong non-Gaussianity. And that's certainly something that we want to worry about in the future. Thank you.
Thank you very much, Valery. So questions, Gia, please.
Hi, Valery.
Hi.
Can you hear me? Yeah.
Yeah.
So this is what so let me try to formulate my question, because it's so I mean, I have this understanding of strong regime of quantum gravity, which I'm pushing for some time, that essentially when naively we enter strong coupling regime in gravity, in reality this simply means multi-particle states, because when the coupling is strong, this means that momentum transfer is high, and actually even a virtual graviton in that case becomes a classical black hole, because it's strong coupling in gravity means strong gravity, strongly gravitating, even virtual graviton strongly gravitating. So there is no object in gravity with energy higher than the Planck mass, which is a single particle state, simply because of property of gravity that it has to accompany arbitrary and high energy source. So my understanding of strong gravity is that essentially what happens is that gravity becomes multi-particle gravity when you try to push it in the strong coupling regime. So essentially it's impossible really to push it to strong coupling regime. So effectively what we need to do, we have to resum the theory. And at the end of the day, so in other words, very high energy gravity comes back to classical gravity because it's fully dominated by black holes. Now in your picture, so in your picture, this is what I'm trying to understand. So in your picture, you are just simply treating, how are you treating, when you're saying that you are extrapolating theory to a strong coupling regime?
What I wanted is to avoid this situation.
So you don't want to enter in the strong coupling.
The effective Planck mass is lower than the all classical scales. So
you mean higher?
The Planck mass is higher than all classical scales.
So you want to avoid entering in strong coupling?
I want to avoid it completely. I don't want to go into super Planckian regime and energy.
So yeah, okay, that's what I understand. So basically your program is to try to never enter in the strong gravity regime, just to eliminate singularity, to avoid singularity.
Yes, exactly.
In that way. So that's the philosophy.
So my Planck mass goes to zero.
I understand. Not to zero, to infinity.
Universe is so slowly expanding that the Planck mass is still very high.
Yeah. So basically, your point is that you can keep universe, you can have cosmology in which essentially all the momentum transfers, in my language, are always lower than the Planck mass at that time.
If I stick to this sector of scalar tensor sector.
Yeah. Okay. Yeah.
Because if I want to consider electrons, then it's another story. But my matter is the electron mass is larger than the Planck mass.
Well, that is a problem. But let's exclude that. That's okay. I mean, let's exclude the electron. I mean, of course, in real gravity, that would still be a problem, obviously, because electrons would be strongly gravitating, etc. But anyway, okay. I understand your philosophy. Yeah.
Mm-hmm. Okay. Thank you. So Christoph is next.
So Valery, as you know well, these things depend quite a lot on the metric frame that you choose. For example, many inflationary models, I have once constructed a primordial flat frame where the Planck mass is proportional to the scalar field and goes to zero. So that would be exactly in your class. Mm-hmm. So you can do the opposite. If you go from your frame to the Einstein frame, how would it look like more a standard inflationary theory or something like that? I mean, the analogy with power law inflation gives, to me, at least a certain flavor. And it would be interesting to know, you know, how things look in the Einstein frame.
You see, it's rather difficult to go to Einstein frame here, but I agree that that's worth trying. But I think it's going to be rather tricky because what I see is that depending on parameters, you may or may not get into quantum gravity regime, which you don't do in inflationary theory. So I think it's going to be quite tricky.
But
Because
I mean,
you know, the interaction terms are quite different from what you have in conventional gravity with the usual sort of Browns-Dicke. No,
We don't hear you, Christoph. Your voice disappeared. Okay.
Christoph.
No. Okay, let's go to Neil's question, and then we wait till till Christoph can speak. So Neil.
Hello, hi Valery. Good to see you. Yeah, my question is more or less the same as Gia's, except I'm not going to let you off the hook. Where does the matter and radiation come from in your picture? And what about electrons and photons?
That's later on. You know, the picture.
Yeah, but how are they produced?
Well, they're produced. Well, you can arrange things in such a way that later on, after bounds, your scalar field is just conventional scalar field, just conventional massless scalar field. And then you go to kination stage where you have, you're dominated by a massless scalar field. And that's K-inflation. That's what people have done long ago to produce particles from this rolling scale.
Okay, so your assumption is that the universe begins in this very empty state where there's only gravity and some other stuff,
right?
Which kind of participates with gravity, and then there's no matter, no radiation, nothing else.
No, nothing.
So how do you imagine justifying that assumption? I mean, it's a...
Sorry?
How do you imagine justifying that assumption? It seems completely unlike...
Why?
Anything?
I think it's very likely that nothing was there.
So you
very long ago, huh?
Aha. Okay. You want to start with a completely empty universe, but not stable. Is that the idea?
Stable. Well, it's not stable, meaning that it does evolve. That's true.
It's sort of minimal, in the minimal possible instability. Is that the idea?
That's sort of, yes.
Okay. All right. Okay. Thank you.
Yeah. Thank you.
Okay. Yeah. Maybe I can ask a question myself. Actually, it will be kind of continuation of what Christoph asked. As far as I understand, if you say that you are in weak coupling regime, then I would say that there should exist some transformation of variables leading you to another frame, whether it's Einstein frame or whatever, remains to be seen, in which this weak coupling is kind of obvious. And I wonder if you try to find out this generic change of variables.
It's a good question. I can't answer you offhand. It may be a good question to try, but once you do your transformation to sort of Einstein frame, things become very complicated. That's for sure. So we didn't try it, and it's not obvious because the whether you are entering what are the energy scales compared to your expansion scale depends very much on parameters, which means that probably things are quite tricky. But that's a good question. Yes, that's a good point.
Thank you. So I propose to, I don't see questions more. So let's thank Valery for the talk. Thank you very much. And then I invite Leonardo, who is here, to share the screen. So Leonardo is going to talk about the Sitter-Noether theorem. Please go ahead, Leonardo.
Okay, So thank you very much for the invitation to this virtual workshop. I was asked to talk about this research line, and I'm very glad to do that. But first, let me just share some of my views on the current status of cosmology. Cosmology is a great subject to study the history of the universe, and in the last few decades, we really had a fantastic incremental from the observational point of view. Really, we got lots of data, and with this data, for example, one of the most important observables was probably the cosmic microwave radiation, where the fluctuations are very small, 10⁻⁵. And we had lots of progress about the understanding of the universe from this. But technically, this result was due to the fact that the perturbations were small. And so instead of solving very hard partial nonlinear equations, we could solve easy linear equations. And also, to generate the initial perturbations that are at the basis of that allows us to evolve the universe in this with this linear theory, there is typically the theory of inflation, which is also a very simple theory. The fluctuations of the inflaton can often be described to an extremely good approximation. Indeed, observationally, we know that this is true, close to at least perturbatively weakly coupled harmonic oscillator. So at the theoretical level, lots of the progress that we had in cosmology comes from the fact that the theory was very simple, and also we had lots of data. But right now we are in the situation where the CMB has almost saturated its information. And since the robust on everything goes down, while like one of the square root of the number of pixels, we cannot expect much bigger improvements apart from maybe B modes. So instead of large-scale structure surveys really provide potentially the next leading source of information. But until very recently, a systematic theory for predicting what was observable was lacking. And really, this is where there is a huge development on the observational side. And I think for the continuation of the cosmological program that I just mentioned, summarized, it's essential to develop such a theory. This is, I think, what we did in the skepticism of the broad community with the so-called effective theory of large-scale structure. And after a long and painful development, I would like to highlight that it's beginning to bear the first fruits. For example, 2 years ago, we were able to analyze, to get all the cosmological parameters from the leading source of galaxy clustering information, which is called the BOSS survey, this Longitudinal Sky Survey. And we measure some parameters already very close to Planck, just using large structure and Big synthesis data, no CMB. And later this year, at the beginning of this year, we were able to get the first and strong limits on primordial non-Gaussianities. These are inflationary non-Gaussianities from large structure. And these results are on the so-called orthogonal equilateral shapes. They are weaker than the one on Planck, but they're not really much weaker than WMAP, which was the former generation experiment. And the BOSS, the data we analyze are old data. Now there are much better data that are being taken from new experiments. So I believe this is very encouraging for the prosecution of the cosmological program as we have experienced in the last 30 or 40 years. It's a lot of work to do this kind of theory. It's a bit like QCD. And so quickly it becomes very painful. We are computing 3-point functions in one loop, things like that. It's very hard. And so I think it's very important. And so that's why I do it, because otherwise there are not really, I don't see how we get more data from cosmology and so more understanding of the theory. But it's very hard. Lots of codes, lots of calculations. So how do we elevate our mind in the meantime? And I think to elevate our mind, we go back to foundational questions. And for example, one foundational questions that some time I go back is how the quantum effects in inflation behave. Often the fluctuations contain the there is a small coupling constant, but then there is a large, potentially large IR divergence. A few years ago, we showed that in inflation, for single field inflation, these effects, the secular growth of the perturbation induced at quantum level, it's absent. But for the case of additional fields, it's actually true that there are these secular divergences. It's true that the theory becomes strongly coupled, the dynamics is non-perturbative. And in the last few years, with Victor, who I think is going to talk about this topic, we show that indeed it's possible to formally systematically compute correlation functions on additional fields in the Cpt space, even in the presence of the non-perturbative dynamic. So I think this is a foundational question that is important to settle, and progress is being made in the last few years. Another interesting topic that is the one I think I'm going to talk today about is the initial conditions of inflation. In fact, for a long time, it was unclear how to start inflation. That is, the reason was that there was, in the case of high inhomogeneities, we had lack of control of our calculations, and this gave rise to many debates in the community, in the public press, for example. Now, a few years ago, we realized that we could use the same codes that are used for black hole mergers, the ones that predict the LIGO, Virgo signatures, to simulate a universe that starts completely homogeneous. So we take a box of universe with a Lagrange of a scalar field, but we take the scalar field completely homogeneous. If you look at the black region here, this black region is the distribution of the energy, and you see that when it's one, it means that it's the potential energy of a cosmological constant, the flat inflationary potential, and then there are many gradients. And now we let it go. I let the universe evolve. And you see that a white region, which means that potential domination is emerging here, while all the inhomogeneities gather here, where now there is an horizon. This is excised horizon. This is a formation of black holes. So we see that in a universe, a box like this, let it go with a very big fluctuation. Indeed, it forms black holes, but at the cost of somewhere else starting inflation. Where there is white, it's actually it's practically the Cpt space. So here we found that indeed the so-called initial patch probability, that is, we had to start inflation, we had to have an homogeneous initial condition, did not seem required. Indeed, we always found in every simulations that inflation was starting somewhere, even though somewhere in the manifold, even though somewhere else black holes were forming. But if the question, did inflation start somewhere in this box? The answer was yes every time. And so, given that these are numerical simulations, we cannot make a theorem which is saying order 1 times, surely order 1 times of the initial condition inflation starts. But this allowed us to refine a whole conjecture that was due to Hawking, even though the one of Hawking we think, at least the one we found, cannot be correct, but refinement of his can be, which is the fact that all initial expanding universes with a positive cosmological constant and with the right topology of the spatial slices, we will reach the Cpt space sometime in the future. And the idea is, can we prove this theorem? Now, what are the topologies that we're talking about? This has been, the three-dimensional topologies has been classified, the proof of it has been classified a few years ago by the famous Perelman, and goes under the name of Thorson geometrization conjecture. That is, all the three-dimensional topologies, compact, can be classified into 3 families. The first are called closed, for example, S3, S2, S1, and compactification. They have the property, in particular, that the metric that one can put on these manifolds, if one considers the Ricci scalar, it can be anything. There is no constraint on it. Then there are, let me just skip to the second, the open one, the open topologies, for example, the compactified hyperboloid or H2 cross a circle, etc., which have the property that any metric must have the Ricci scalar negative at least at one point in an open set. And then there are intermediate, which are called the flat, like the torus, where there are R3, if you take a metric on it, R3 will have the following property. Either is negative somewhere, or it must be 0 everywhere. These are, and then these are there are about 8 topologies that classify, that are the fundamental set of the topologies into dimensions, and one can form different topologies by gluing them. And so the number of topologies is actually equal to the natural numbers. But the property is that when you glue manifold of different classes, one goes in the resulting manifold is in the lower classes. So there is a sense in which for most topologies are the so-called open kind, that is must have R3 negative somewhere. And by the way, this was something noticed, for example, by the string theory community, but okay. So we're going to use this result, which is a famous result by Perelman. Here is in the picture, but we're trying to use it to handle analytically spacetime window symmetries and potentially singularities, similar to what was done by Paneros or Rodolu. As I said, we use exactly this classification, this topology, this result on topology and geometry. And also we use something else, which I'm going to explore, which is a particular flow, which is a result in differential geometry called mean Kubota flow. And we're going to show that for most topology, indeed the so-called open kind that I mentioned before, the universe must keep expanding somewhere with a higher rate, and so expectably it will go to the Cpt space. And this, in fact, it's a research line that involves interesting also mathematicians. For example, here in pink are my collaborators with seats in math departments. In fact, let me comment about this point. That is, I think it's an interesting connection between mathematics and physics, in particular the field of differential geometry, which is a very active field in mathematics. For example, but normally what they do, they deal with stability of spacetimes. In a sense, very famous in the last few years has been the stability of the black holes, of the Schwarzschild metric, the Sitter-Schwarzschild in particular. But when they talk about stabilities from a physics point of view, it's less exciting because they know what they have at hand. Or often, like Paneros, they often have bad things must happen, like singularities. And often, for example, they use flows, but they study these flows, geometric flows, for their own sake because they like the flow. Vice versa, in cosmology, we almost always deal with small fluctuations. We know the asymptotic regime, and therefore we know the asymptotic regime of the universe up to that small correction, which we study with a great deal. There are two exceptions to this point. One is eternal inflation, where quantum effects completely change the space-time. And the other is the epoch prior to inflation, which is the topic I'm talking about here. Here, the space-time is quite unknown, and we wish to explore it, but maybe there will be singularities. We don't even know where they are. So there's a pressing physical questions, which I think is much more interesting from the mathematical point of view, because it's a much more, in a sense, wild, the setting of manifolds we're dealing with, and the mathematical questions. For example, the setting we have in mind is the following. We're going to start with some initial two-dimensional slice, and the universe will evolve in time, and maybe there will be singularities, and we want to know if in some regions, a region like the Cpt space, so infinitely large, will develop. But notice that the question is complicated because we want to do it with general Lagrangians, at least as general as possible. So, for example, we can have aliens, nesting aliens, going around. And if you have a nesting aliens, where it sits, the stress tensor is non-zero, so it cannot be the Cpt space. So that point. So if I'm going to converge in some sense to the Cpt space, it must be in some sort of way, okay, which must be able to handle this kind of small defects. So here I'm going to present some progress in this direction. It is the Herdesky theorem for cosmologies with isometry group forming two-dimensional orbits. And let me explain. So let me start from the limit of homogeneous cosmology, which was proven by Wald in 1983 that if the stress tensor satisfies the dominant energy conditions, all the homogeneous but anisotropic universes, the so-called Bianchi universes that are not closed, that is not type 9, and with a positive cosmological constant, go to the Cpt space, point-wise, actually. Now, the dominant energy condition means that for any time-like vector, the minus T mu nu K nu is Fisher-directed time-like. This essentially means that there is not superluminal propagation of momentum. Then we're going to assume this. We're going to also assume the weak energy condition, which is T mu nu T nu for T mu time-like is positive. Essentially means that the energy density and the energy density plus the pressure is positive. And also we're going to assume the strong energy condition for the method. That is this combination of the stress tensor for K mu time-like is positive, which basically means that gravity is attractive for one source by the stress tensor. Notice that we're going to assume this for the stress tensor. Many of these are violated by the cosmological constant, particularly strong. But actually, only the strong. But we're going to say that there is a cosmological constant plus something else. Okay, so usually these energy conditions are not loved by the physics community because the cosmological constant violates them. Otherwise, I think they're pretty fine. And here, indeed, we're going to say there is a cosmological constant and the rest satisfy this. So I think this is quite, at least personally, I find it okay. So all the homogeneous cases already prove the theorem, but I want to highlight that in the case of homogeneities, the situation is incredibly harder. From the mathematical point of view, the differential equation go from being ordinary to partial, but also singularities cross, cross, and maybe singularity forms. Okay, so even physically, the situation is extremely harder. And let's try to set up the problem, and let's consider general cosmologies. So what does it mean to have a general cosmology? So, okay, let's set up the assumptions. The first assumption is that we consider a connected 3+1 dimensional space-time with a compact Cauchy surface. So a compact Cauchy surface is simply because to make the problem very well defined. I mean, it's even simple. The situation, I think, it simply generalized to the non-compact case. Now, if you have this, at least physically, if you have this setup, Gerok in 1970 proved that the topology of the space-time is M cross R, where M is a three-manifold. And this manifold can be foliated by a family of topological identically Cauchy surfaces, quite intuitively. The topology cannot change, otherwise it wouldn't be a Cauchy surface. The second assumption we will do is that meta satisfy dominant and strong energy condition, on top of having a cosmological constant with positive value. And the third assumption is that the special topology of these slices, which I remind you is the same at all times, is not to be of the closed kind. That is, the topology is not of the type 1 of the Perelman torso classification that we discussed before. Now, in 2+1 dimensions, if we were living in 2+1 dimension, actually the theorem that initial surfaces will go to the zeta space has been proven. We proved it. And here, in 2+1 dimension, the Gauss-Bonnet theorem in 2 dimensions for the spatial slices, which are 2-dimensional in this case. And also in 2+1 dimension, the fact that the Riemann is known in terms of the Ricci tensor played a huge simplifying role. So, though it's quite an untrivial statement, it's simpler. And unfortunately, also accidentally, we do not live in 2+1 dimensions, so it's not as interesting. So, let's move to 3+1 dimensions. And indeed, we had already a first result, which is valid in the absence of any symmetries, which is the following. Given this kind of hypothesis, there cannot exist a singular space-like upper surface with maximum volume. That is, given anytime slice, there is another slice with larger spatial volume. Furthermore, if the universe is initially expanding everywhere, there is an initial slice which is expanding everywhere, then there must be at least one expanding region at every time slice. In any time slice, there is a region which is expanding, and if lambda is bigger than 0, then the spatial rate is in that region is larger than what would have been the zeta space with the cosmological constant. So in other words, this tells us that given a universe that is initially expanding, some region keep expanding as fast as there would be the zeta space. So so that there is always a volume slice with larger volume. So this strongly suggests, at least to me, that these slices will reach infinite volume because the derivative is positive. Okay, that doesn't. It might go to zero, but the derivative is positive. So the volume grows, gradient energy will dilute, inflation will start. No matter the initial homogeneity and the scale of inflation, this suggests that inflation will happen, or the zeta space will happen. But it does not prove this. Okay, this is the result is only the one stated. Now, in order to show this result, let me set up some notation. So imagine that we have a three-dimensional slice with the normal vector, time-like. Here it is, a normal vector. The four-dimensional metric is the three-dimensional metric, is g mu nu minus mu nu. And the statistical curvature is this gradient of the normal vector, which has a part which is the trace part, k, and the anisotropic part, sigma mu nu. The statistical curvature tells us how much the flow induced by the geodesic is divergent. In particular, the trace k is tell us about the rate of growth of the volume. The volume grows like this. In an homogeneous universe, k is essentially the Hubble rate. Now, let me just show you the formal result. Consider the Einstein equation, g mu nu equal a pi g t mu nu, and contract it twice on the normal vector on the spatial slice. But the Gauss-Codazzi relation, this tensor can be written as a combination of R3 and K square and Ks, which are three surface quantities, the statistical curvature. Therefore, this Einstein equation becomes this. Now, we want to ask, is there a surface with maximal volume? If there is a surface with maximal volume, better be that I cannot deform it and let the volume grow. Therefore, since the growth of the volume is the trace of k, then better be that k is zero everywhere. So if such a maximal surface exists, must have k equals zero everywhere, and so this must be true. But clearly, this is negative, and if I apply the weak energy condition, this is positive. So for this to be true must be that R3 must be positive everywhere. Otherwise, I cannot satisfy this inequality. But indeed, as I showed before, there is indeed a topological condition that tells us that on any three-dimensional slices, depending on the topology of the three surfaces, but for most of these topologies, there must be at least one point where an open neighborhood where R3 must be negative. Around that point, this cannot be true, and so this surface cannot exist. And so this proves the theorem that there cannot be a maximal surface in this kind of topology, so the volume can grow. There is always a surface of larger volume, and trivially one can also prove the statement about the growth rate of those small regions, potentially small regions. As I said, these results suggest the existence of the theorem that for the moment we haven't proved it in generality, and we have proven such a theorem that the universe will go to the zeta space in the case of an isometry group imposing some symmetries. Here, the symmetry we have improved is that there is an isometry group that will form two-dimensional orbits. We have partial results which involve less isometries, but I will talk about this in a different time anyway. There's still work in progress in that sector. But just to say that this might not be the end of what we can do. So the setup we're working on now is that there are all the assumptions that I said before about the cosmology, the topology of the slices, and the stress tensor satisfying the energy conditions. Here we're going to assume a fourth assumption, which is that there is a symmetry group G which acts on these spatial slices, is such that the action on the full spacetime is by isometry. Is such that the orbits of this symmetry group are closed surfaces. So this is the mathematician way is to say that we consider a universe where the spatial slices have homogeneous but potentially anisotropic surfaces, and these surfaces foliate the three-dimensional slices. So let me take a picture. So of the spatial slices, there is a spatial slices. There is these circles are two surfaces. They are homogeneous, as you can see from this figure. But on the third direction, which is a circle, there is an homogeneity, and these points are identified. So not all topologies can allocate such symmetries, but for example, can allow such symmetry, but for example, the torus, H2 cross 1, H2 cross S1 can do this. So many topologies can allow for these symmetries. And the theorem we're going to prove is the following: if the two surfaces, these two surfaces here, these circles in the figure, if the two surfaces have non-positive error characteristic, that is, they're not two spheres, but in the case of two spheres, if they are initially large enough, and also if the initial spatial slice is expanding everywhere, so the sensitive curvature is positive everywhere, but otherwise incredibly inhomogeneous, then asymptotically the space-time becomes physically indistinguishable from the Cp space on arbitrary large regions of space-time. And this is all true, notwithstanding the presence of initially large density fluctuation and potential singularity, and also notwithstanding the presence of potentially the aliens and things like that. Notice that from the physics, while in the cosmological setting, it might not be very satisfactory to assume that there are some initial symmetries. For example, this initial assumption about symmetries is very good to explain experimental facts, like condensator capacitors in electrodynamics, because there is the experimentalist building the symmetric capacitor. Here in the universe, not quite.
Yeah, you have 5 minutes.
Oh, I see. Okay, so here it's a bit not so interesting, but notice that the statement is that from a not very symmetric situation, we're going to reach a situation where there is an incredibly larger symmetry group, from the two-dimensional isometries to the full symmetry group of the Cp space. Okay, recently we generalized some of partial result, making without the dominant energy condition. Let me skip this. We get a weaker result, but we get some result. But let me just explain a bit the main results. So now we need, I explained already the notation. Now I need of the three-dimensional surfaces. But now the way we're going to deal with the problem is that consider the three-dimensional surface, and there is the two-dimensional surface here inside the three-dimensional slice, and the three-dimensional method can be written as h mu plus T mu, where T mu now is the normal to the two-dimensional slice inside the three-dimensional slice. And clearly there is an extrinsic curvature associated to this to the flow of this T mu, which tell us how the surface deform as we move the surface inside the two surfaces inside the three surface. The method we use is what is called the mean curvature flow, which is the following. Taking a three-dimensional slice, we are gonna deform it forward in time if it's positive, the sensitive curvature is positive, and backward in time proportional to the sensitive curvature if it is negative. So K times the normal. That's the deformation of the slice. Notice that the volume under this deformation, parameterized by lambda, is now, if you change the volume form, it goes K because that's the change of the volume, but then we change proportional to K, so the volume changes like K squared. So given a slice, one creates a slice of larger volume. And this is at the basis of lots of physical intuition, which is the following. This flow is extremely regular in 3+1 dimensions if you start from three slices, spatial slices, because the flow wants to increase the volume. But in Riemannian geometry, if you have a curve, you want to increase the volume, you just do this. So a very singular surface has lots of volume. But in the semi-Riemannian geometry, if you try to do that, you go through null. You take a specialized surface, in the middle it's null, but null has zero volume. So this cannot be done. It will actually decreases the volume. So what the flow starts to do is just to stretch the surface and keep it regular. So with this intuition, actually one can prove that the flow stays regular at all times. And this is extremely useful because it's an instrument to prove results. Also, we want to prove results where there potentially are singularities, but we don't even know where the singularities are. But all singularities that we know of, physically interesting singularities, have the property that they're crashing. That is, as you approach the singularity on spatial slices, you can foliate the Cauchy domain of the singularities, then the volume goes to zero as you to process singularity. In particular, the extrinsic curvature of the slices goes to minus infinity. And one can prove that the flow, the mean quantum flow, will not hit the singularity, so we stay a finite distance away from the singularity, because the singularity is zero volume, and the volume was to grow in the flow, so it will just not go there. So this can be proven rigorously, okay? And another theorem one can prove is that given a slice with some extrinsic curvature, there will be a maximum on the extrinsic curvature, and on each surface since it's compact, there will be a maximum on the extrinsic curvature. And one can prove that the extrinsic curvature of the flow actually decreases up to the extrinsic curvature of the Sitter space. That is, the maximum of the slices actually relaxes to the maximum rate of the rate of what would be the Sitter space. And the proof is very simple. It's a simple application of the maximum principle. One look at the evolution equation for the extrinsic curvature says, oh, what about if there is a maximum? Well, the maximum of the Laplacian is zero. If the maximum is larger than k lambda, this is positive. This is positive, okay, so the derivative must be negative, okay, it will decrease. Things like this allows us to prove that the extrinsic curvature will go, the maximum must go down, zero. So let me show you the basic step of this proof in the remaining 2 minutes. So we're going to prove that there are regions in this manifold which asymptotically become physically indistinguishable from the Sitter space. In a certain way, right? Because, you know, this surface starts inhomogeneously, so something will remain inhomogeneous. The point is that there will be a region here which blows up and becomes indistinguishable from the Sitter space. Even though between here and here is not like the Sitter space, there will be a long delay, there will be something in the middle, okay? So the first step is to prove that these surfaces, in particular the minimal surfaces, grow with the rate of what would be a slices of the Sitter space, or the 2 slices of the spatial slices of the Sitter space. Then one also proves that the transit direction grows like the Sitter space, and then the volume grows like the Sitter space. In particular, one can show that the rate of growth of the spatial slices is actually very close to the Sitter space almost everywhere, because k cannot be too different than k lambda, the Sitter space rate, and sigma, which is the anisotropic part, can be small, because this grows like e to the 1/3 k lambda, but the volume goes like e to the k lambda. So that's the first step. So geometric quantities grow. Then we define the metric, this metric here, which is this metric here, just letting grow with the rate of the Sitter space. And one can show that the actual true metric, asymptotically from some one time on, one makes this definition some late time. If you want to make this definition a late time late enough, then from then on, the actual metric and this blow up with the Sitter rate, actually they're very, very close. You can make them point-wise arbitrarily close. So that's the second step. 5 steps and that's it. Then the next step is to say, okay, but this metric is not the de Sitter metric, right? Because the initial metric was very, very deformed. It's not de Sitter, it's highly homogeneous, just blow up. But it's quite intuitive to say that given that it's blow up, then if you take a neighborhood here and you let it grow with the Sitter rate, as will be the Sitter rate, then within this ball, a late time, with this 3-dimensional ball, actually one can show that the metric, the actual metric of the flow, is very close to the one of the Sitter spacetime. This is Euclidean spacetime, this one. Again, starting late enough. From some late time on, the difference is going to be very small for all, arbitrarily small for all times. This is about the 3-dimensional slices. One can go then to the 4-dimensional slices, which are the one really induced by the flow. The flow has a time coordinate. One induces a very natural 4-time for metric, for space-time, 4-dimensional metric, which is minus k square here, the lambda square, where lambda is the flow time, and then spatial slices. And one can consider the analogous de Sitter metric, which is this one. We already showed that on these balls here, we found the green region, where practically like the Sitter space points. On the time direction, actually, it's not true. There are some times where k is very different from k lambda, so it's not true that this point-wise convergent. But one can show that the integral on any geodesic, only time like geodesics, the length of any time like geodesic between 2 points, if the geodesic is late enough, starts then late enough in the future, then it converts to the Sitter space. So any geodesic looks like the Sitter space. And the last point I want to say is the following. So geodesic looks like the Cp space, but what about matter? One can show that the integral over the volume or over one slice, because the two-dimensional on the surface is trivial, the integration, the integral over any component of the stress tensor actually is bounded. That is, if one imagines to be an experimentalist, one finds himself in a region of space, and the geodesics are the same as the Cp space. So in particular, there is an horizon. So the observer can only access a small region of space. In this small region of space, the integral of the stress tensor on any component of the stress tensor in this region actually becomes arbitrarily small as it starts later and later the experiment. So there is really nothing to make the experiment with. So the experimentalist will conclude, or the alien will conclude that she is in the Cp space. And so, but at this point, we have shown that the geodesic are the same, the space-time causal structure is the same as the Cp space, and the stress tensor is physically the same as the Cp space. In a subtle sense, right? That is, point-wise, there could be some stuff, but for any integrated quantity, physically integrated quantity, there is nothing left. And I think I'm out of time. So if people ask, I can present some step of the proof. Otherwise, I would simply stop here. And sorry for having not perfectly organized time.
Thank you very much, Leonardo. So Christoph, you can unmute yourself. Please go ahead. We don't hear you, Christoph. You're muted.
I'm not.
Yeah. Now you. Now
okay. So Leonardo, quite interesting. I'm used to think in terms of correlation functions. What about a simple situation where the average value or the mean value of the metric goes to 0, and the correlation functions, the 2-point functions, stays non-zero? I mean, that's in a certain sense my preferred scenario. For example, the mean value of the metric follows de Sitter space, so it goes to 0 in the infinite path, and the correlation function is just finite. Of course, the relative inhomogeneities will diverge in this case, because you compare the 2-point function to the value of the metric. Is that simple scenario compatible with your findings? Did you ever think in terms of correlation functions, or do you mainly concentrate on particular geometries?
Sorry, I'm not sure I understand. Your question was about the past, right? Here we're talking
yes,
about
I'm going to the past. So in the past, let's say you go to a situation where the mean value of the metric in a quantum theory goes to 0. That's perfectly fine. And the correlation function stays finite. So it becomes obviously very inhomogeneous. If you look at forwards in time, it's the opposite. Forwards in time, you start from something very inhomogeneous, and then the expectation value grows, and once it's large enough, it will dominate, and the universe will become homogeneous and look like inflation. Is that compatible with your picture?
Yeah, so I think physically it is compatible. I mean, we're getting the standard de Sitter, for example, in this geometry, in this case here, we're getting the standard de Sitter space. Now, technically, we cannot answer your question in this setup for two reasons. First, the mean Kubota flow is a flow defined forward in time. We cannot go back in time. Okay, you can make statement only in one time direction. It's like a diffusion equation. Second, physically,
but that's fine. I mean, you start with some given fixed correlation functions, take a few representatives, and then look if the expectation value will finally dominate and be something like the Sitter.
Yeah, and that's yes. Okay, the answer is to that, yes. Now, if you go forward in time, the answer is yes. Now, technically here, it's all in classical geometry, and these are very rigorous proofs, okay? So it's very hard. That's a very interesting question. I'm talking to these people in the geometry community to rigorously show results, to talk about quantum mechanics, quantum field theory in in this kind of setting. It's very hard, frankly. I don't know how to do it without a certain background geometry, and then I quantize. I do first order, kind of weak field quantization on top of that. Here we start with complete inhomogeneous universes. So technically, your questions I cannot answer, but you see, I think physically you start with something inhomogeneous, you let it go, you reach a classical de Sitter space. Quantum mechanically is going to be the same. That's my expectation.
Okay, thank you, Leonardo. Enrico, you can unmute yourself.
Yeah. Hi, Leonardo. I had a question about the issue that you were calling the aliens, just to understand better. So if I'm I am an observer on Earth. In my asymptotic future, I would imagine the metric is something like a Schwarzschild de Sitter, in which if I'm close enough in units of the mass of my galaxy, I see more of a Schwarzschild metric. And if I'm further away, closer to the horizon, I see the de Sitter metric. How do you define this average?
No, because here there are two. The symmetry group has two isometries, right? So it's more like the observer is kind of a domain wall, a brain, okay? And because of the dominant energy condition, it has to dilute. Matter has to dilute. So your question is right, but it does not satisfy. So the situation cannot arise in the case of in the symmetry group and satisfying dominant energy condition. So that's why there is pointwise convergence of the metric to the spatial slices, because even on this domain wall, you might expect that there are discontinuities of the metric, and but with such a symmetry group, it cannot happen.
I see. But
with less symmetries, it will happen. Mm-hmm.
Okay, but pointwise.
In fact, sorry, let me add one more thing. We even prove in this kind of isometries, we prove that there will not be singularities. The space-time is actually geodesically complete. We do not assume it, but we prove it. So it's a bit disappointing that once we put two isometries, there cannot be singularities. Now we have partial results with less symmetries, and then there can be trivially one can see that there are these singularities, and some statements can still be made.
Okay.
Did I answer?
Yeah, thanks.
Okay, thank you. So, Suksi, you can unmute yourself. Please go ahead.
Thank you. So, question: what is the relation between this mean curvature flow parameter, so the evolution there, and physical time evolution?
Very good question. So, yeah, indeed, some oscillatory results that we get here is that the time of the flow becomes very similar to the time of locally defined de Sitter space in FRW slicing. Up to there is a trivial factor of K lambda, but apart from a trivial factor, this flow time here, but you almost see here, right? The metric here, this is given there is the flow here, you can define a four-dimensional metric on the slices, and the time the lapse is this. But K is almost K lambda everywhere, almost everywhere. Indeed, we show that it's almost everywhere, almost every time. And so, yeah, the time tends to be that. So this flow tends to asymptote to the FRW slicing of the Sitter space at that time. So it's really ideal, seems to us, ideal to prove this theorem that because it tends to behave like the Sitter space where the universe is like the Sitter.
Yeah, but the flow is driven by this mean curvature flow equation, which is different from the physical time evolution. So understand that if you take this lambda, then you get something that looks like a physical spacetime. I'm asking what's the relation to the real physical evolution of the spacetime, which is given by the Einstein equation, not by this mean curvature flow.
So yeah, maybe I wasn't clear. Sorry. So two statements. First is that we can show that the flow actually foliates an arbitrary large range, because you might wonder if the flow stays there all the time. Instead, that the flow keeps going and actually foliates through the flow in arbitrary large region of space-time. And then the idea for us is to, which by the way, in the math, the mathematicians, collaborators tell us that this is a new application of the flow, because the mathematicians were studying the flow for the flow's sake. But here we use the flow to study the geometry that satisfies Einstein equation. That is, we don't care of the flow. Okay, the flow for us is an instrument to move ourselves around in this manifold. And by the way it moves, we learn about the geometry. Okay, so we prove that it moves, so it doesn't get stuck, but it moves in a way that doesn't hit the black holes. So good, it moves and we can. It stays away from the bad regions, but moves inside the de Sitter regions. And when it moves, we can conclude, for example, that the universe looks like de Sitter space. Did I answer your question? Because I don't see your face. So yeah, did I answer your question?
So.
Yeah, but it doesn't show all the.
Yeah. If you understood it, then I didn't understand. I was not satisfied with the answer, but we can discuss later, because I still don't understand if this is really the time flow that you're discussing of. This is something that you interpret as the time
flow. I don't know. I don't know how to say more than to say that I'm not talking about the flow. I'm talking about the metric of the space-time that satisfies Einstein equation. Is my answer clear?
No. But
okay.
When you move on this, let's move on. Let's move on.
Okay, I don't see more questions, but you guys can get together in some of the rooms. Okay, so thank you very much, Leonardo. And if you can stop sharing the screen. And so next talk is by Neil Turok. So Neil, please go ahead. So Neil is going to talk about new boundary conditions for cosmology. You can share your screen.
Okay, I'm trying to share my screen. Okay, that's good.
Yes, so we see something.
Great. Okay, thank you very much, and thank you to the organizers. I have to start with something a bit awkward, but we do live in the real world. We may feel it's unfortunate sometimes, but I have to start by expressing my profound opposition to the invasion of Ukraine, and of course solidarity with both physicists and non-physicists there, and also with those in Russia who are perhaps unable to properly express their own opposition to what's going on. So I just felt I had to say that. Of course, very happy to discuss with people in the breakout sessions. I'm going to talk about adventurous topic, which is really to re-examine the foundations of our understanding of cosmology. In a certain sense, the last 40 years, which we've been following a certain track, which is to add complication upon complication to known physics. And over the last 5 or so years, I've become unhappy with this. And I have the feeling that we may be missing some very simple points, which when properly understood will make things make sense without us having to add lots of complications. So this work is done with Latham Boyle at Perimeter Institute and based on 2 earlier papers. So let's just look at where we are in cosmology. Observations have really given a huge surprise, which is that the large-scale universe, very far from being a complicated place, is remarkably simple. And so far, the data is extremely well fit with just 5 parameters, one of which is very small anyway. 3 describe the energy content, baryon to photon ratio, dark matter to baryon density, and the density of the dark energy. And 2 describe the perturbations. These are very nearly perfectly scale invariant. So in terms of the curvature of co-moving slices, the RMS curvature goes like k squared times some potential. And this potential has a nearly scale invariant power spectrum. The amplitude is around 10 to the minus 4. And this slight tilt is just over 1%. Very many quantities are consistent with 0. No tensors, no isocurvature perturbations, no spatial curvature. It's a remarkably simple universe. And so what I'm going to explore in this talk is the possibility that actually this simplicity we see in the universe is a manifestation of how the universe came into being. And in particular, there's a possibility that the universe was extremely simple at the Big Bang singularity itself. And that's what I'm going to explore. Roger Penrose has captured this rather beautifully in this picture, that while general relativity allows arbitrarily complicated geometries, somehow the creator of the universe ignored all that and created a very special geometry which Euclid would have been perfectly happy with, just flat three-dimensional space. And why did the creator ignore all of those possibilities? So I want to draw an analogy, which is with the flatness of the Earth. We're all used to the fact that when we use a map of our hometown, and here is Edinburgh, we don't need to worry about the curvature of the Earth. Flat space is, flat two-dimensional space is a perfectly good description, as long as we don't go very far. And if you look at this picture of the Earth from space, it's locally very flat. The surface of the Earth is very flat and very smooth. And why is that? Well, naively, you might say, to explain this, you might either say, oh, there was some mechanism whereby the Earth was created in this perfectly round state. So on the one hand, you might say, like Valery, that the beginning of the universe was this extremely special, perfectly spherical state. The beginning of the Earth was just spherical because spheres are nice. Or you could say that we're going to introduce a mechanism like inflation. And here's my mechanism, which comes and hammers the Earth into a perfectly round state. Neither of those are very good explanations for the flatness. There is a very good explanation for the flatness, local flatness and roundness of the Earth and smoothness of the Earth, which is just that the Earth is very large. It has about 10 to the 50 atoms. And then secondly, the physical laws which make it round are gravity, which pulls the matter inward, the existence of dissipation, so that if a mountain collapses, it doesn't bounce back, and thermodynamics, in other words, entropy. So if you consider the ensemble of possible geometries for the Earth, and including very complicated geometries, spiky geometries, for example, you will discover that they have much lower entropy than a round Earth in which the energy, the internal energy, is distributed as heat among the atoms of the Earth. So here's an explanation for geometry, which is very compelling. It's based on very few assumptions and then on thermodynamics. And I should mention that there recently is even observational evidence in favor of this explanation, namely that the mountain ranges we see on the Earth occur in places where there are graphite layers, essentially produced by the first plankton, which sank to the ocean floor and were compressed into graphite. And graphite is an excellent lubricant. And so when the continental plates drifted over the surface of the Earth, when they collided after this graphite formed, they formed ridges and large mountain ranges. So when you remove the dissipation, indeed, the Earth becomes less spherical. So the key point here is to do with measures. And I want to emphasize that any proposed solution of cosmological puzzles, for example, horizon, flatness, homogeneity, lambda, always rests on some perhaps intuitive notion of a measure, how likely a certain geometry is, or a distribution of matter, or a parameter in the laws of physics. If you don't know what the measure is, you're always on shaky ground. And unfortunately, that is the case for all current cosmological theories. is that the measure is seldom explicit. So where do these measures come from? Well, in physics, measures arise from quantum statistical mechanics. Quantization allows you to count states, and when you can count states, then you can assign probabilities to states and deduce some kind of most likely measure subject to constraints. So the main question is there a quantum statistical mechanics for cosmology? And I'm going to propose one, which is remarkably simple. You may not like it. You may find it's too magical, but it is unambiguous, based only on Einstein's gravity and simple assumptions about the matter. And it gives remarkably interesting results. Where does this measure come from? So it's inspired by the work of Hawking and others on black hole thermodynamics, which of course is still only partially understood, but for which there's a great deal of evidence, both from real black holes in the universe and also from analog black holes and experiments on analog black hole systems. So just to remind you, Hawking inferred that the temperature of a black hole is inversely proportional to its mass, then that the entropy of a black hole is proportional to the mass squared, or the area. I'm always going to use units in which h bar c and kb are 1. And so the Planck mass is 1 over 8 pi g, and Planck mass squared is 1 over 8 pi g, and the Planck length squared is 8 pi g. So that's the inspiration for the measure I'm going to use. Now, there is a well-known gravitational entropy associated with de Sitter spacetime, and this was inferred using essentially the same methods that were developed for black holes. And it's inferred in a surprisingly elementary way from the Euclidean path integral. So one considers Einstein's gravity, one then considers a cosmological constant, and no other matter in the universe. And then the unique solution of the, let's say, empty Einstein equation, so no gravitational waves, is de Sitter spacetime. And then you say, well, how do I construct a Euclidean path integral which corresponds to this de Sitter spacetime? You send the time in the closed slicing to minus I times the Euclidean slicing, and de Sitter space turns into a four sphere. And then the exponent is in the path integral becomes minus the Euclidean action. And this is just the Einstein-Hilbert action, appropriately Euclideanized, and the density of the cosmological constant, representing the lambda. And so just working out the solution of the Einstein equation, which is the continuation of de Sitter space, is a four sphere. Taking the trace of the Einstein equations, you find that the Euclidean action is negative, and it's given by this well-known formula, inversely proportional to rho lambda. For today's value of the cosmological constant, this, and then one interprets the saddle point in the Euclidean path integral as giving the entropy of the, so the path integral gives the exponential of the entropy. And this entropy is a few times 10 to the 122 for today's cosmological constant. By the way, this derivation hides a very important sign, which I'll mention later, that in fact both signs are possible, both plus and minus, and of course with such a huge entropy that makes a very big difference. But this is the calculation of the entropy of de Sitter space. Now what I'm going to do is generalize this. We don't live in de Sitter space, we live in a universe with the radiation, matter and lambda, and I'm going to generalize it to a universe which just has radiation in addition to the lambda. See, at very early times, the radiation dominated. At very late times, the lambda dominated. The matter era is really a sort of addition in between, which or let's say a complication in between. We live in the middle of this complication. But as a first approximation, it's reasonable to pretend that the universe just has radiation and lambda. And that is successfully described the early stages and the late stages, as far as we know. So then I'm going to assume normal cosmological metric. I will, towards the end of the talk, discuss perturbations of it and how they affect the entropy and so on. But for the moment, let's just begin with assuming FRW symmetry, and then we will generalize it later. So I'm going to take the spatial topology to be compact, just so that the volume of the universe is finite and all of my calculations will be finite. But actually, the precise value of that volume won't matter too much in anything I say. And I will allow the curvature to be either positive, negative, or zero, and consider all cases. So here's the Friedman equation in conformal time, that the time derivative of the scale factor squared, I'm here taking 8 pi g to be, well, I've rescaled units, as you can see. So here I have the radiation, which just plays the role of a constant. I have the spatial curvature, which comes in as a squared, and then the cosmological constant, which comes in as a to the fourth. Apparently, it wasn't noticed that this equation has a very beautiful solution, analytical solution, which is that the scale factor is a Jacobi elliptic function, which is a simple generalization of the trigonometric functions. And this function has remarkable global analytical properties. And that will actually be the inspiration for this talk. It's a very elementary point. That solution to this semi-realistic cosmology really takes a remarkably simple form. And I should say that these global analytical properties do extend when you include matter, but it complicates the analysis. So I won't do that. So here's the general solution for all values of radiation, curvature, and lambda. And here's what it looks like. So the scale factor turns out to be single valued in the complex T plane, conformal T plane, no branch cuts. It's really very beautiful. Near the Big Bang is a simple zero. The scale factor vanishes linearly in T. And then future infinity is a simple pole. In de Sitter spacetime, A goes like -1 over, 1 over T star minus T, where T star is the limiting conformal time at the future infinity of de Sitter space. There are other solutions. There's a closed oscillating universe, which I think Friedman first wrote down. And there, of course, is de Sitter space, which would bounce at finite scale factor. So these are the general solutions. The only singularities in this scale factor are simple poles in the complex plane, and it is doubly periodic in the complex plane. Now, periodicity in imaginary time implies that there is a Hawking temperature. And again, this doesn't seem to have been noticed before our work. We pointed out this in a recent paper. So this semi-realistic universe has a definite Hawking temperature. And just as in black holes, once you have a temperature, you're tempted to ask questions about the thermodynamics and the entropy. And that's exactly what we have done. So let's see. Now, notice that, you will have noticed that I am dealing with singularities here. This is a cosmological singularity when the scale factor vanishes. It's a very simple singularity. The metric goes to 0. It's analytic, meaning the metric is an analytic function of the time, but it is a singularity. Now, we proposed dealing with these singularities previously in our work on CPT symmetry. So we again noticed that this initial singularity is a simple 0 in the scale factor. And we actually used this to argue that we could calculate the density of right-handed neutrinos, even though they were never in thermal equilibrium. And we calculated them essentially from this Hawking temperature of the cosmological spacetime. And we therefore used that to solve the dark matter problem. So this CPT symmetric universe, our idea was that, and by the way, I should mention this was anticipated in a paper a long time ago by Andrei Sakharov and by others. This idea was that the universe is symmetric under CPT. What does that mean? It means that before the Big Bang, there was a mirror image of our universe in which the matter was actually antimatter. And if you try to put it together in a single picture, it's a bouncing universe, but one which goes through 0 scale factor. Our understanding of this picture now, so the equations of motion are analytic at the singularity, even though the equations are singular, and one has to deal with this singularity very, very carefully. In our new work, we argue that, in fact, the Big Bang singularity behaves like a perfect CPT mirror. In other words, there are two ways to describe it. Either you impose a boundary condition at t equals 0, a very specific boundary condition, or you extend the picture to using effectively a method of images and consider states which are perfectly symmetric. And those states have analytic evolution through the singularity. In fact, our idea was anticipated quite a long time ago by Newman, who was a postdoc working with Roger Penrose. Roger Penrose had speculated that the Weyl curvature would be 0 at the initial singularity, but not at future singularities, like the ones inside black holes. And that was related to the arrow of time. What Newman showed is that if you couple general relativity to a perfect conformal fluid, i.e. radiation, perfect radiation with traceless stress tensor, then the full nonlinear Einstein equations have a well-posed Cauchy problem where the initial data is precisely the conformal 3 metric at the singularity. So he made a very similar analysis to ours, but he studied the conformal 3 metric at the singularity. And the 3 metric alone defines the full future evolution of the 4D spacetime. This was our explanation of the dark matter. We took one of the right-handed neutrinos. Of course, it is introduced in the standard model to explain the small masses of the left-handed neutrinos. Naively, there should be 3 right-handed neutrinos, and you only need 2 of them to explain the observed neutrino mass differences. There are 2 parameters there. But so it's very natural to suppose that one of the right-handed neutrinos is the dark matter. If you want it to be the dark matter, you have to turn off its decay process through the Higgs, for example, by imposing a Z2 symmetry at tree level. And if you make it stable, then of course, now it doesn't interact with any standard model matter. So it was never in thermal equilibrium, but it is produced by essentially by the time dependence of the background metric in the universe. We calculated its abundance and we found it fits the dark matter if this is its mass. And there's a prediction of this setup, which is that if it is stable, then then one of the left-handed neutrinos must be massless, and that will actually be observationally tested in the next few years. So let's go back to StatMech for cosmology, and let's assume, I'm going to now assume these CPT symmetric boundary conditions, that the Big Bang is a conformal zero in which the conformal factor has a simple zero at the Big Bang. And let's try to do statistical mechanics. Well, the first issue is, in that picture, we obviously have two different temperatures. There's the temperature of the radiation, which goes up to the Planck scale at the singularity. And even today is much larger than the de Sitter temperature, which is minuscule. So there are at least two temperatures in the problem. Second issue is that the Hamiltonian is zero in general relativity. So a priori, you think you cannot define a canonical ensemble. How are we going to do thermodynamics? Nevertheless, you can still define a statistical ensemble. I want to make the point that statistical mechanics, in principle, has nothing to do with equilibrium. It's just a statement about the most likely set of states subject to certain constraints. So even if you're discussing a non-equilibrium system, providing you can clearly describe those constraints and you can examine all states which satisfy the constraints, you can certainly do statistical mechanics on that on the set of states. Now, there's something which helps us a lot in cosmology, which is that the expansion of the universe is adiabatic. The Hubble constant is much smaller than the temperature of the radiation, except when you're right at the Planck mass, very close to the Planck temperature. And because it's adiabatic, the radiation in the universe is very close to local thermal equilibrium. And so if we treat the universe as just containing radiation and lambda, it's very reasonable to treat the radiation as being in local thermal equilibrium and to treat it as a perfect fluid.
So you have 5 minutes.
Okay. So we're going to use the path integral. I will skip over this just to advertise a forthcoming paper on real-time path integrals, which are somewhat delicate to define, but can be defined, and partition functions. So the distinction is very important. In the former case, you can never get positive semi-classical exponents. And this is actually we use to argue against the no boundary proposal. In the latter case, you can only get positive semi-classical exponents in partition functions when the Hamiltonian is zero. So, okay, I won't go through this in detail. I will just say one integrates over the radiation, noting that the radiation entropy is an adiabatically conserved quantity, and there is an associated internal energy. And then we essentially perform the path integral over radiation, leaving us with a path integral over gravity, with this action in which the radiation only appears as a constant. So that's a well-defined action. And we now discuss its equations of motion, its dynamics. Again, I won't go through this. This is very standard cosmology. We have a closed universe, which expands and collapses. We have de Sitter space, and we have the universes which come out of a Big Bang or collapse to a Big Bang. So this is the complete set of solutions. We now go Euclidean. So it turns out there are two ways to go Euclidean, either the usual Wick rotation or a Wick rotation combined with a conformal rotation, that the scale factor also gets an I, and we call this CW. And then, so here's the usual Wick rotation. This suffices to describe a universe with a small amount of radiation. It's basically like de Sitter space, but with a modest amount of radiation in it. And the limit is the Einstein static universe. If you put more radiation in, you get more solutions, ones with Big Bang singularities. And these solutions correspond to different instantons. And what we noticed is that if we do both rotations, we get instantons for all values of the cosmological parameters, whereas the usual Wick rotation only gives instantons for a very restricted set of parameters, which are unrealistic from today's observations. So today's observations correspond to parameters which, for which you need to do this other Euclideanization. The solutions are very beautiful. They are, again, Jacobi elliptic functions. We can calculate the Euclidean action analytically. This is the functions in the complex plane of their argument. The instantons are topological, namely the functions essentially live on a torus, and the instantons correspond to the action for paths which wrap around this torus in a non-trivial way. Here are the solutions for all values of the parameters, and here are the results. So on the bottom axis, we have the entropy of the radiation expressed in units of the de Sitter entropy to the 3/4 power. If we think about today's universe and the entropy we already see, that is approximately 10 to the 90. So this number is of order unity in what we already see. Okay. On the vertical axis, we have the total gravitational entropy, which we calculated in units of the de Sitter entropy. And what one sees is that basically if the universe is substantially bigger than what we already see, and by substantially, I just mean, say, 10 times bigger in radial extent, then we would be we'd be way up here. And the gravitational entropy would be considerably larger than the de Sitter entropy. Okay, that's our main result, is that as you increase the radiation, actually the entropy goes down when you're in something looking like de Sitter, but it hits 0 at the Einstein static universe and then rises. And for negative curvature, it rises all the way. So in particular, this scaling I've mentioned, you can understand very simply in terms of number of horizon volumes. But here's the punchline. If the total gravitational entropy of the universe, in other words, the total number of degrees of freedom in gravity in the universe, if this total number is just 1,000 times the de Sitter entropy, i.e. the universe is roughly 3 times bigger, roughly 10 times bigger than what we see, then the most probable universe is flat, okay? Because here I'm graphing omega in curvature, the term in the Friedmann equation representing curvature, over the term representing the density. So what we find is that providing the universe has a large number of degrees of freedom, just analogous to the number of atoms of the Earth, if the number of degrees of freedom is large for gravity, then the most probable universe is actually spatially flat. We've analyzed the scalar, tensor, and conformal perturbations. They all decrease the gravitational entropy, and therefore the most probable universe is homogeneous, isotropic, and flat on large scales. So if you believe these boundary conditions, if you believe the calculations of the entropy, the answer is actually very clear, that the most probable universe is flat. And just like we see. Much remains to be done. We have to explicitly construct this quantum ensemble and show these instantons are its saddles. We haven't done that. It looks like possible to do. We have to generalize this to non-conformally invariant matter and include black holes. One can study string theory as a 1+1 dimensional model cosmology, and there are very nice string models with exactly these features, a Big Bang and a horizon, and they have so-called gravitational entropy. There's also, how do we get the perturbations? We have a new way to do this consistent with this picture, which I will talk about in the future. Thank you very much.
Thank you very much, Neil. Questions, please. Yeah, Sebastian, please go ahead.
No, sorry, I was just clapping.
So you don't want to ask the question. Okay, then Martin, you can unmute yourself.
Yes, hello. Thank you for this very nice talk.
Thank you.
Could you shortly explain what would change if you would include the matter dominated period, or what would qualitatively change?
Yeah, so it actually changes remarkably little. So when you introduce matter, for example, you would put a scalar field with a mass. And what happens is that this field, there's a new scale which enters, which is the mass. So as you follow this massive scalar field, the same is true with the right-handed neutrino, by the way, it has a mass. And so what happens is that as you follow the evolution equations of these fields across the singularity, they oscillate. Just a finite number of times, but they oscillate. And so the matter density is not a simple power law, and therefore the evolution equations for the metric are more complicated. So as far as we can see, there's no, basically whenever you get the mass, it comes in as the mass times the scale factor. So the mass becomes irrelevant at the singularity, but away from it, the mass is causing the field to oscillate. That's in the conformal conformal time frame. And so the mass is a complication, but it doesn't seem to affect the picture strongly. Black holes are, of course, much more challenging. How do you analyze black holes? What I would say is that this initial condition that the metric is a regular 3 metric times a vanishing conformal factor, that initial condition excludes black holes. So the initial condition removes any initial black holes just by fiat. Okay, and so the only way you can form black holes is in the late universe by the collapse of perturbations. And again, this seems to be consistent with what we see. So we are imposing a very strong initial condition, and that plays a very important role in preventing the universe on large scales just being a single black hole, for example.
More question. Well, there is a question on the chat from Lucy. Okay, I can perhaps read it. I may have missed this point early in the talk, but do you intend to include a phase of inflation, or you are proposing this explanation as an alternative solution to the problem solved by inflation?
Yes. Our motivation is to replace inflation with a much simpler theory. What has happened to fundamental physics? I think in the last few years, we've seen great simplicity in the large-scale universe, surprising simplicity and economy, and the same on small scales. The LHC discovered the Higgs boson and nothing else. And personally, I think we should learn from that I think particle physics, theoretical particle physics, has gone through a phase where people proposed more and more complicated models with more and more parameters. I think that's heading in the wrong direction. What I have decided personally to do is to focus on the laws that we know, namely Einstein gravity and the Standard Model, and to see if we can't interpret them in such a way as they would naturally explain everything we see. We don't have so much to explain. The universe is incredibly simple. So I've more or less taken it as a rule of my work that I am not going to introduce a single new particle, okay? And I think that's a very useful discipline. Now, maybe it will fail. But actually, since we adopted this point of view, we have made, I think, quite surprising progress. And I would refer you to another paper of ours, one of the ones I mentioned, where we explain the 3 generations of elementary particles just on the basis of the consistency of the Standard Model with gravity and conformal invariance. So what we pointed out is the trace anomaly due to standard model fields can be cancelled if and only if there are 3 generations of elementary particles. So this was a big surprise. It does involve some additional assumptions, of course, but it's a very different way of doing physics than just to add an extra field and parameter and potential. It's really trying to re-examine the foundations as a means of solving, as I say, these problems in cosmology, which after all are extremely simple.
Yeah, thank you, Neil. Yeah, I have a question myself. So you say that your initial conditions are CPT invariant.
Yes.
So my question is how stable the statement is. So if I have a deviation from CPT, is everything fails or everything converges to your picture?
Everything fails. So yes, so I think it's taken us some time to come to this point of view. One could imagine a universe in which the 2 halves were were identical at a classical level, but distinct quantum mechanically, right? And so they could have different fluctuations, for example. The more economical point of view is that the 2 versions of the universe, before and after the Big Bang, are really the same thing, just mirror images. And that's the point of view we have come to. It is more economical, certainly, because then you, in a certain sense, you don't really have a pre-Bang universe at all. All you have is a mirror image of the post-Bang universe. And I find that quite compelling. There is an analogy with string theory. I mentioned this briefly. I won't put the equations up. But in string theory, one has open strings as well as closed strings. And open strings have sort of a boundary, where there is a certain type of reflecting boundary condition. And it turns out that the Big Bang singularity in GR is really analogous to that. And our interpretation of it is essentially that the Big Bang singularity is the analog of an open string boundary condition. So, of course, the difference is that it's in time, not in space. And that introduces additional subtleties. So that's the point of view I want to explore, that really there is only one universe. It came out of the Big Bang, and there was a very special boundary condition at the Bang.
Thank you. So I don't see more questions. So thank you very much, Neil.
Thank you. Thank you.
And yeah, so this closes the morning for Europe session. Okay, and we leave this. Yeah, so we leave this site open, and there are